All right, welcome everybody. Today we are very happy to have Diego Villamizar from Tulane University, who will talk to us about a refinement of d-Dyck paths.
Okay. Yeah. Thank you. Thank you all for coming. Thank you for the organizers, especially Eric and Sandra, which are the only ones I talked to. But thank you all for coming. Yeah. So I'm gonna talk about the work that we did with Rigo, which is in the audience, Jose Luis and Fabio. Jose Luis and Fabio are actually back in Colombia, and we have two things in common. The things in common we have is that we actually like studying some statistical properties of combinatorial objects. And the second thing we have in common is that all of us are Colombian. And right now, Colombia is not a very happy place. And so I wanted to bring that into attention before I started, because it's something that I believe must be known. And we have been two weeks in protest, a week and a half, barely. And there has been a lot of police violence in this protest. It's basically a consequence of economic bad decisions as a consequence of the virus. So there is a lot of unrest there. And a lot of innocent people have died, and there is a lot of people missing. So I just want to, I mean, I don't have time, of course, to tell you all the details, but I just want to encourage you to read about it. So I have these two hashtags here that you can go and to Twitter or to whatever you get your social networking and read about it. And if you know of someone that is in Colombia, a friend, a family, or a colleague, and you care, you should probably express your support to them. And I just barely want to say something on this image on the left. Is that this is the colors of the flag of Colombia. So Colombia has three colors. Yellow, that means richness. We used to have a lot of gold, and it's usually the biggest one. So this flag is distorted in the proportions. The second one is blue, which we are very proud of our water resources, because they're very important for us and for our biodiversity. And the third color is red, from the blood of the liberators, I think is the right word in English. And it's usually very small, but right now is very big, because of all these people that is fighting for our rights and is fighting for having like equality and justice. So yeah, I just wanted to bring that into your attention. But I guess I will start speaking math. If you want to talk about this or about the math, feel free to contact me or email me or whatever you want. Okay. So I'm going to talk about some statistical properties of a very specific combinatorial object, which is d-Dyck paths. d-Dyck paths are lattice paths that live in the first quadrant, as you can see. And the steps that you can make are either diagonal up or diagonal down to the right. And so they're going to be labeled as X for this kind of diagonal and Y for this kind of diagonal. So you see the arrows pointing the direction of it. We're going to call also P. So P is going to be a path, and also P, we're going to call it the semi-length, which means essentially how many X's or how many Y's does the path has. Okay. And I mean, we all know that this is a very well-known study object. Probably we all have read about it. There is this book that has like 100 ways to do bijections with this object. And so the common denominator of all these objects is a sequence of numbers called the Catalan numbers, which have this form. And there's also a lot of ways to show this form from the d-Dyck path. So the number of d-Dyck paths of semi-length n is given by this Catalan number n. And one of the important or useful things that you can do with sequences is to store them in a formal series. So this is something that we usually do in enumerative combinatorics. We just put all the sequence as coefficients in a formal series, and we treat the function that we treat formally the function doing some arithmetics that represents some combinatorial information at the end. Okay, So for example, if you notice this generating function has an equation that is satisfied, and this equation is symbolic for a kind of factorization in the path, in the d-Dyck paths that we will talk about. Okay, this is pretty well known. So for example, if I want the paths of semi-length 4, then these are all of them. I think there are 14 of them, which is this number over here. Okay, so you can see you never go outside first quadrant. So you can imagine the coordinate at the like the coordinate center at the first vertex, if you like to call that like that. And these are all. Okay. So the thing that we want to study is some parts of the path, and we are going to try to put some characterizations on how we would like our paths. So to understand that, we need to know some basic terminology on these paths. And so, for example, we have the peaks, and the peaks are these parts of the path that are like the little peaks, like in a mountain, and they are marked by circles. And then also they have valleys here, and I mark in the valleys, I mark the height of the valley. So if you treat this as x equals 0, then this is sorry, y equals 0, this is y equals 3, this is y equals 7, this is y equals 10. So what we do is we record these numbers and we call it the valley vector of the path. Okay, so we record this. Of course, this is not enough to just contain the whole path. So we can have different paths that have the same valley. We will need to record the valley and the peaks to be able to completely characterize the path. So this gives us some freedom in the sense that we now can say, so we now have like two paths going to the same vector. So we can have some kind of property in the vector to be represented by a bunch of paths. Okay, so that's what we're going to do. So the basic definition that we will be presenting is the so-called d-Dyck paths, which are some kind of restricted Dyck path. And the condition is that the path has either 1 or 0 valleys. So either it's a complete peak or it just has one valley. Or if it has more than one valley, then the valley vector should have this property, that the two consecutive terms in the vector differ by no less than d. Okay, that's why it's called d-Dyck path. And d for the first part of the talk is going to be positive, and at the end of the talk, I'm going to talk about what happens when d is negative. Okay, so we denote this set mathcal d, the paths of semi-length n. So we do it for every semi-length. So this is all the d-Dyck paths, and these are the d-Dyck paths of semi-length n. Okay, and some basic properties that you can follow from the definition are that if you take the ones that, so if you have the property that they differ by greater or equal than k plus 1, then they of course differ from more or equal than d, but of course they are not all of them. Okay, so this happens for every k. Also, if you make this go to infinity, then this second condition is never met. So the only condition that you have is this first condition. So we call this v sub less or equal than 1, which means paths that have just 1 or 0 valleys. So they are not that hard to count. So we discuss them. And then we have the case in which that we make d go to minus infinity. When d goes to minus infinity, then we have complete freedom of the valleys. And when we have complete freedom of the valleys, well, we recover all the Dyck paths. So we recover Catalan numbers. Okay, so these are very basic properties out there. But now the question is, what can we, so can we count these paths? Okay. Okay, for example, here are the Dyck paths of semi-length 4. So all of these are the Dyck paths of semi-length 4th, but the ones in black are the 3 Dyck paths. The other ones, you can notice that this, for example, these two valleys, the distance is no more than 2. This one is no more than 2, etc., etc. Okay, so these you have to discard in the count. Okay. Okay, so there has been some work before this. So the work that has been done started in 97 with Austin and Guy, and what they did was they studied non-decreasing Dyck paths. So non-decreasing just means that d is equal to 0, so they cannot go down, never. They just go up, or they stay in the same level. And what they did was they used generating functions also to count that the number of 0 Dyck paths of semi-length n is equal to the Fibonacci number at 2n minus 1. Okay? They use generating functions for this. And they did some other things related to the area of the paths and things like that. We actually do also things like this, but I'm not going to show it for things get very big, and I don't want to, ruin your lunch there. So later on, and now this is part of Rigo's work, 2015. This person, which I don't know how to say his name, so I'm not going to try. I'm sorry. And Rigo, and this is also a Colombian person, which I don't know how to say his last name either, so I'm not going to attempt. So, but you can read it. What they did was they filtered this result in the sense that they subdivide these Fibonacci numbers in the ones that had exactly some number of peaks. Okay, so the peaks in the paths have to be exactly s. And what they did is that they discovered that this is exactly this binomial number here, and this is essentially what we're going to try to do for the general d-Dyck path. Okay. So 3 years later, these same 3 authors and then Jose Luis showed that now that the total number of peaks, so what they do is just they sum over all the paths and they count all of the peaks. One of the things they did was they found that that number is equal to this number here, which I think is very pretty. Is some kind of linear combination on Fibonacci numbers. And they also other results that they have in that paper is that they actually count peaks in a height in a fixed height. Okay, the formulas get a little bit more complicated, so I'm not going to show it. But they actually did the counting for all of the Dyck paths, all of the peaks in the 0 Dyck paths at some height, at some fixed height. Okay, so this is what has been done. What has not been done is the general case for D, and this is what I'm going to show you. Okay, so the first case that we're going to deal with is the case in which D is positive. So to be able to say something at the beginning, just as in Catalan for what I told you about the generating function, what we have to do is we have to find some kind of factorization of the paths. And this factorization using the symbolic method will allow us to say something on the generating function. Okay. So we call this delta pyramid. And so a pyramid is just in images. You see my mouse, yes? I'm just moving my mouse and okay, cool. So a pyramid is a triangle that looks like this. Okay? A maximal pyramid is a pyramid that you can now extend further. So for example, this over here is a maximal pyramid. Okay, and they have the description is just you go up a number of steps and you go down a number of steps, okay? Consecutively. T denotes another non-empty Dyck path. So the idea is to decompose the Dyck path that you're working on in previous paths, okay, to be able to get some kind of recursion. And so the result is that you can take any of these Dyck paths and decompose it in one of these cases. So you either can have a path that looks like this, of course, or you can go up and go down and put any Dyck path that you like. So this thing that looks like the little prince hat is another Dyck path, d-Dyck path. Or it can be like you go a little bit up and it has a pyramid, and then you go down and then you go these steps up. So now this is the condition here, okay, because this is a valley, so we have to maintain this condition. And then you put any d-Dyck path that you would like here, and then you have to go down. So this corresponds to this string here, okay? And the last one is this one, which corresponds to you go up, you have a pyramid, you go down, then you can go up as much as you want, except that you cannot surpass d because of the value. Okay, so you have these four factorizations possible. When you construct them symbolically, you get the recursion, and with that recursion, you can say the following. You can say that if you consider the generating function of non-empty Dyck paths, so this lambda means the empty Dyck path of semi-length 0, when you add over x to the power of the semi-length and y to the power of rho of p, and rho of p is the number of peaks of the path. So we are actually having two statistics, the semi-length and the number of peaks. Then using this decomposition and using the symbolic method, you can compute this function here. Okay. So of course, if you take y and you replace it by 1, then you just have your semi-length, and you will be able to recover the number of d-Dyck paths for d positive. Okay, so we have a generating function. But at least for me, I like enumeration, so this is a little, I mean, it's great, we have it, but looking at this doesn't give me a lot of satisfaction. My other colleagues really like these expressions, but I really like to see the formula. Okay, so that's what I'm going to tell you now, how to find the formula. Okay. So to be able to find formula, we take the problem and we describe it in strings. So we take a d-Dyck path, and what we do is we try to express it as some binary words that are called d-restricted words that were studied by Austin and Guy in the 70s, I think. And this will allow us to count them. Okay, so strings are way easier to count than these paths, so we're going to try to do it. Of course, strings can be tricky too, but these ones are very nice to count. Okay, so the definition is that if you a d-restricted word is a binary word in which the ones appear in blocks, appear in chunks that are separated by zeros, and the condition is that each of these chunks should have at least d characters. So it should have at least d ones. Okay, and what we do is we call this VDN to be the number of the restricted words of size n. If you're familiar with this, this is a machine that accepts the numbers that are given by this expression. What this does is that you take your string and you say, oh, I need some kind of machine that tells me if this word is good or not, and you feed it to the automata, and then if the automata ends up here, so by following from left to right the word, you follow the path in a graph, and if you ended up here, then it's because it was a nice word, it was a d-restricted word, and if you don't end up there, it's because it was not. Okay, that's just that. But this characterization of the words in this graph, the nice thing about them is that there is a technique called the Chomsky-Chatzenberg technique that let us construct a generating function of the number of words accepted of some length, some fixed length, by solving some equation on the, so there is like a symbolic relation in between the graph and some system of formal power series. And so you can get that the generating function for these d-restricted words looks like this. Again, it's really nice, but I'm not very happy with that because I really want the numbers. I really want the at least a binomial or something. So what you can do is you can actually take d-restricted word x and you can factor it in some way. And you can factor it by taking like maximal chunks of the same character, okay? And you have some conditions. Of course, the condition on the d-restricted word is that if you take the chunk of the ones, then this b sub i's should be greater or equal than d. And for example, if you take these zeros that are labeled by a, so this means a2 copies or ai copies of 0 in a row, then this a sub I should be greater or equal than 1, and this ones that are in the extremes of the word, they really don't matter much more because there's no blocks in there is no chunks of 1 in between them, so they really don't matter if they are 0 or 1. And when you have these things, then you actually have 3 compositions of numbers. You have a composition of ones when you recover the b sub i's. You have a composition of the zeros when you recollect the a sub i's, and you have a composition of the c's. And after some kind of Vandermonde style sum, you get this over here. Okay, so this makes me at least a lot happier. I know that this is much more complicated from a recursion that you can find from here, but this gives me more satisfaction. So I cannot leave you without telling you that. So this is the number of d-restricted words. Okay. And something that is interesting here is that even though that this is a sum, you can actually say something about just the summand. And this summand in K just means something about the number of chunks of ones here. Okay, so this K actually says something about the number of chunks you have in this word. Okay. So I tell you something about some words that came from nowhere. So what does this has to do with the d-Dyck paths? So to be able to say something about the d-Dyck paths, what we did was we found a correspondence in between the d-Dyck paths and the d-restricted words. And it seems easier for at least for us that it's easier to explain the bijection when you take your Dyck path and you express it as a tree, as a plane tree. So there is this correspondence in between Dyck paths and of semi-length n and plane trees of number of vectors equal to n plus 1. Okay, and essentially the correspondence is you take a tree, and what you do is you transverse the tree in, I think this is pre-order, yes, in pre-order way, in pre-order transversal, and you go recording when you go down and when you go up. If you go down, this corresponds to up steps in the path. So for example, this up, down means this, up, this up means this down, 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 etc. Okay. This is like the first exercise of this huge book. I mean, it's a little book, but it has a huge exercises from Richard Stanley on Catalan numbers. You can go there, and they have actually some little snake going around here. I like to call this it looks like a ghost to me, but I guess to him it looks like a snake here. Okay. Okay. So this is the first step. The first step is you take your path and you convert it into a tree. Why? Because it's gonna be easier. Okay. The second thing that you have to do is, well, okay, so this correspondence is for the whole Dyck path, but that's not very good because we have so we have a subset that we want to study. So we need some conditions on the tree that represent the conditions on the path. And it turns out that the conditions that you need are the following. First, this is the image for you remember the 3 Dyck paths that I showed you? There were 7 of them from the 14 that I showed you at the beginning. So you mentally can do so like this one becomes this mountain with 1 peak, and etc. etc. So mentally you can get an idea of which ones are these in the paths. And the conditions essentially are the degree, so these trees go from up to down, so they're rooted here. And so the out degree just means that the number of vertices that are below the vertex V are connected to the vertex V, but below it can either have degree 0, 1, or 2. Okay, so you either can have a leaf here, so this has out degree 0 because there is nothing below, or you can have a degree 1. For example, this one here just goes 1. This looks like a line there, or you can have 2 of them. So for example, this one. So notice that I'm going to go into the other slide. So notice that this one has 3. So this one is not there. Okay, and it's not there because you see here that this thing makes the problem that there are 2 of them consecutive here in the same height, and you want to avoid that. Okay. So the first condition is that, and it's because of that. It's because you will get a bunch of paths in the same height that you want to avoid. The second condition is that no vertex of degree 2 should be on a left induced sub 3 of any vertex. That is because if you have so if you have two vertices and one is on the left of it, is because so first before saying this, just notice that when you do this bijection mentally, the peaks are given by these leaves, yeah, and the valleys are given by these two 2-degree vertex. Okay, so if you have one on the left, then it just means that you are having the condition that the one on the right is lower than the one on the left, and you want to avoid that because the distance will be negative, and we are dealing with D positive. Okay, so you also want to avoid that case. And the last case is that if you have two vertices and they have degree 2, so I don't have an example here, but later you will see, then the distance in between the two of them has to be greater or equal than D minus 1. And this is like the important condition for the positive. If you have two vertices there, they have to have some distance, because we want to have some distance in the valleys, and the valleys look like the two vertices there. Okay. So, and actually, these three are conditions that they have to satisfy, but they are the only conditions they satisfy. Okay, so it's equivalence there. Okay. So the last step is to take a string and try to decompose it in this tree. So what you do is, for example, I give you this this string here. I think we're taking D equal to 3. So for example, you see that the chunk has 3 ones and a little bit more than 3. This has 4, which is greater than 3, and this has 3, which is exactly 3. Okay, and what you do is the following: you take your you start from left to right. So what you do is, if you see a 0, you go down. Whenever you see a chunk of ones, you take the first D of them and you put it in a degree that splits, and the rest of the ones that can be 0 or more go to the left part of the tree. Here, you don't put anything in the vertex that is here, so it can be a leaf or it can be not a leaf, but it has to have degree 1, because remember that there cannot be a degree 2 on the left, so it has to be degree 1, and so it's here. And you don't put it in this degree, you put it in the other ones. If you see zeros, you go down to the right. The next time you see the chunk of ones, you put the first D on the vertex, etc., etc. So you keep doing that, and what you ended up having is that this string corresponds to this corresponds to this tree. And by the look of it, it's very clear that if you get 1 tree over there, then you can do the opposite thing. So this is bijection. So this is very good news, because we took paths, we converted them in trees, and trees converted to strings. So we have that strings are the same that paths. Okay, and we know how to count strings. So now we know how to count paths. Okay. So the result is that this VD, which is the number of D-restricted strings of size n, is equal to the d-Dyck paths of this distance here. So this is just technically in the number of vertices, but it's not very important. The important thing is that they two are related to each other. Okay, and so we have bijection between these two, so their cardinals are the same. But because we know how to count these strings, then we know how to count this thing here. So what we get is that the number of d-Dyck paths of some length n is given by this formula. Okay. Again, this is very satisfying from the enumerative point of view, and perhaps also from the arithmetics point of view. No, but I guess it's more satisfying from the arithmetics point of view. Is more satisfying this, but at least from the enumerative point of view, it's very satisfying to have this formula. But you also, with this decomposition, can show that this thing is the solution of this recurrence. Okay, and this is very good for computation and for arithmetic properties of these numbers. If you notice, there is this base case, and this base case corresponds exactly to the v less or equal than 1 that I showed you at the beginning. So the way to think about this is that this 1 is the mountain that doesn't have any valley, and this n choose 2 you should think about as n minus 1 choose 1 plus n minus 1 choose 2, and it's just choosing either if you have a value that ends in the height 0 or you have a value that doesn't end in height 0. If you have a value that ends in height 0, you just have to choose one number, the first number of times that you want to go up. You can do that in n minus 1, choose 1. Or you can choose two numbers, one greater than the other, in the sense that you first choose the ones that you go up with the biggest number that you choose, and then you go down with the less number that you choose you choose, and so you will get 2 peaks there. So one value there. Okay. So you should think about this base case as the v less or equal than 1. Okay. I don't know if there is any question up to there. Awesome. Okay, so remember that in the first thing that we did, we were interested in this generating function that actually had two variables, and the variables were on the semi-length. They were counting the statistic of the semi-length and the statistic of the peaks. So it would be nice to have some kind of a statistic in the peaks. And so what can happen is that in the base case, in the case b less or equal than 1, which corresponds also to n being less or equal than d, you can count the total number of peaks on dd of semi-length n to be this number here. And by the combinatorial interpretation that I just give you of the base case is not very hard to see. And sadly, or I mean, it's very nice, but sadly we don't have like a formula, at least from the numerative point of view. We don't have a formula for the peaks when n is greater than d, but we have a recurrence relation, and the recurrence relation is like this, and it has this base case. Okay, so this is for the number of peaks. Okay, so of course, when I introduce you this, the parts of the path, then you probably observed that if you have, say, k peaks, then you have k minus 1 values. So the number of values and the number of peaks are related, and the relation is that if you want to count the number of values, well, you take the number of peaks and you have to subtract 1 per path, so you will get that the solution of this recurrence relation minus the number of d-Dyck paths that we know a formula of gives you the number of values in the total set. Okay, and a very nice result that all of my other co-authors got in the paper before was that if this is equal to 0, this actually corresponds to this beautiful expression here, where L is the Lucas number, which is like the Fibonacci, but with some switch base case, and this is Fibonacci. Okay, which I think is very cool. Okay. So now we move to the case d equal to minus 1. So now we know everything that we wanted to know about d greater than 0. Some of it we can do better, but that's what we have for d greater than 0. So what do we know about d less than 0? And the case d equal to 0 is the one that people studied before. So we just need the case d less than 0, because remember that what's happening is that when you make d go to minus infinity, you recover the Catalan number. So we want to really try to understand how is that you recover these Catalan numbers. So what is different when you do d equal to minus 1? What is different is the following. So in the factorization of the path, these three first objects that you observe here were also in the factorization for d greater than 0. And there is no problem with them because they can go up. So there is no value here, there was no value before the path, and there is, of course, no value before this. But the problem now is that you can have a value at some height before the value at 0. Okay, so in the factorization, if you want to factor by the last value at 0, then you have to take into consideration that you could also have had a value in the path to the left. Okay, and that is like the difficulty now. Okay, so what we do is we treat this as we treat the ones before, but we give this factorization a name, and we call it Q. And so Q is the minus 1 d paths with at least one value whose last value is at 0. So exactly this drawing over here. Okay. So if you do a mental shot of this these paths, then you will see here that this is xy, this is x t y, x parameter y, blah 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 blah. Okay, so this is what happens here. So the equation that you get is that L on x and y. So remember that y is the number of peaks, x is the semi-length, is equal to this blue part that I put it blue because it is like the previous case, and this part in red, which is what it adds the little spice for d less than 0. And so what happens is that we have this q, which corresponds to the counting for the set mathcal q that I showed you before. And you can have some relation in q, and the relation in q looks like this. And the problem with this is that in this relation of q, you actually have a square. So the nice rational functions that we were getting for the positive are just not possible for the equal to -1. Now we will have algebraic things. And this is very interesting because what it's saying is that if d is positive, everything is going rational, rational, rational. And then at -1, it flips. And it becomes algebraic, algebraic, algebraic until it hits Catalan numbers. And that's going to try to show you a little bit after. And so as a corollary, if you replace y equals to 1, then we can count the -1 big paths. And this is the formula, which, yeah, again, not very satisfying, but it is. I mean, it gives the numbers if you expand this. And I put this in blue because these are the first 4 Catalan numbers. So what's going to happen is that the Catalan numbers will appear as a I forgot the word, as a prefix, at least for the generating function. They will appear one by one, one by one, one by one, one by one, one by one. Okay, and this is what I want to make explicit next. So I want to be explicit on that, but for that we have to talk about the case d less than -1, which is a very hard case, at least for us, and it goes as follows. So what you do is you extend this definition of q, and so so before the q was the last value, it has at least one value, and the last value is at height 0. Now you can have a last value at height I. Okay, so we denote this by, or the generating function, by q sub I. So this is the height of the last value, and this e just is the absolute value of d, just for simple, just to have it positive. Okay. So you define this to be the generating function for the paths in d minus e, okay, with the last value at I, height I. And so what you do is you construct this summation of them. So they are either you do not have any value, or your last value is from 0 to e minus 1. Okay, so you construct this s. So it's either no value, which corresponds to the generating function, or the last value is at height less than e. Okay, so remember that e is the important parameter in these d-Dyck paths. Okay, and what happens is that you create a very huge and messy system of equations. So L is going to have this form. So L is going to be this part, which is like the part before, but it's going to be altered by this S, and that's what it makes it algebraic, the S part. And the S part, remember, that contains all of the QIs, and then you will have a system of equation in the QIs in which you will relate a QI with QI minus 1 and QI with all of the QIs. So if you notice, because S sub E contains all of the QIs, then each of these equations is going to be the solution of the other ones plus some. It's going to be a quadratic equation. So it's going to be algebraic, at least. It's going to be algebraic on the other polynomials. And so you get this. Okay. So I guess this drawing here is to show you that, for example, if you take Q sub I, this part is just taking Q sub I minus 1, because if you are at height I, you perhaps used to have something at height I minus 1, and then you add a height, like one step here. Or you have this case in which you have something in S, which means a path, and then you have a path that ends at I. Okay, and that happens for all of these guys from 0 to e minus 1. Okay, so now you have to solve the system, and the problem is that we cannot solve the system. And the only thing that we can say is that if you are careful with the computations, you can have this L sub E having this look. And if you are like me and try to forget about this Q sub E's, then if you make them 0, you will see that you will get Catalan numbers -1, which is the void path. Okay. So what's happening to the Q sub E's is that they are going to 0 as E goes to infinity. Okay. So this is what's happening after you cross the barrier of D equals 0. So you go from, again, you go from rational to at the point at 0, which is like very nice Fibonacci, and then you cross it to the algebraic part. Okay. And so a question is, what is this Q sub E minus 1? We actually have no idea. For example, Q sub 1 looks like this. Okay, that would be a nice problem if someone knows. Okay, I guess to finish, in the abstract, I said a connection to other objects. So I guess I had to do some connection with other objects. And so what happens is that Cn also counts the number of non-crossing partitions on n elements. If you don't know what that means, you put your elements in like points, and then if they are in the same block, you trace a wire diagram, and they cannot touch each other. Okay, that's the non-crossing part. And this is where this is the word I come from. I come from set partitions, so that's why I'm mentioning. So what we do is with the bijection from the d-Dyck paths to the non-crossing partitions, then you can have a condition on these d-restricted paths. So you can have the d partitions, the d non-crossing partitions, say NCD here. And the condition gets translated as that if you write your partition in this normal form, which means the minimum of this is less than the minimum of that, that is less than the minimum of this, that is less than the minimum of that, then in the block B sub I, you have at least d elements bigger than the maximum element of the next block. That's the condition of being d-Dyck. Okay. And just for fun, what we did was we dropped the condition of being non-crossing, and we translated to the not natural, but I guess classic notion of partition. So if you write your partition now, it doesn't need to be non-crossing; it can be whatever you want, and you put the condition. What you get is this recurrence over here. Okay, and what's very interesting on this recurrence is that if you make d equals to 0, you recover the classical recurrence for Bell numbers. So for d equal to 0, you get the Bell numbers. And so you actually, because the number of non-crossing partitions is less than the number of the whole partitions, then this is the cheapest way I know to prove that the Bell number n is greater or equal than the Fibonacci 2n minus 1. Because this was the 0 case, the 0 Dyck paths, and they corresponds to the non-crossing partition 0, and this corresponds to the whole set. And what happens when d goes to infinity is that if you assume that b sub d of a negative number is 1, which is not a very strong assumption, then you'll see that this will go to 1 when d goes to infinity, and you just get 2 to the power of n minus 1. And morally, what is happening is that this n to the power of n minus 1 can be explicitly written in Stirling numbers of second kind, which are the filtration of these Bell numbers with the number of blocks. And they're greater or equal than this filtration here of the 2 to the power of n minus 1 also in binomial numbers, which used to correspond to the values less or equal than 1. So there should be something going on, as is going on with the Catalan, there should be something going on also in the sense of partitions that is just characterizing d greater than 0. We have not done anything for d less than 0 in this case, and it was very nice to know what's going on there. Okay. With that, I guess I will finish with some reference. Thank you so much for listening. I don't know if you have questions.
All right. Well, thank you very much, Diego. Are there questions?
I just have as a non-generating function person, just a question. Can most of your generating function results be phrased as recurrence type results on
Yes.
these? Okay.
Yeah, so you remember the factorization? So the factorizations of the paths give you some recurrence that you solve in terms of generating.
Right.
Yeah, thanks.
I have a maybe related question, which is that when D is positive, you have these generating functions, and then you also have these recurrences. And generically, you would expect the solution to a recurrence to be something involving the roots of the characteristic polynomial. But in fact, you have somewhat nicer formulas, which are just sums of binomial coefficients.
Yeah,
So was that, are we lucky in that sense, or is there a reason to expect that?